So last time we defined exponential functions as functions that would be of the form y equals a times b to the x. And we'll continue to do that, but we might write the parameters a and b using different letters or in different forms. Um, for example, let's say we're going to let a be 1,000 and b be 1.10. And you can think of this as, let's say I invest $1,000 and I'm able to get a 10% interest rate. Okay. This equation, in this equation, the 1,000 is how much you're investing, and this 0.10 here, that's representing the 10%. The 1 is basically there to keep track of how much you started with. The 1 times 1,000, that's the amount you started with. The 0.1 times 1,000, that part's going to tell you the interest that you're earning. Okay. So for example, if x equals 1, y would be 1,000 times 1.1 to the 1, okay? Well, 1,000 times 1.1 is going to be $1,100, okay? So after 1 year, what happened? You earned $100 in interest, 10% of the 1,000 you started with, and you still have the 1,000 that you started with, okay? So, this example basically can be used to think about all kinds of exponential functions. Okay, generally, whatever the b is, okay, b can always be thought of as 1 plus r, where r is a percent but in decimal form. So you can think of 100r percent is the percentage growth rate. Okay. In our example with the 10% interest, R was 0.1, 1.10 is our B, the 0.10 is the R. Okay. So if, as in a previous example, B is 1.10, R is 0.10, and 100R percent would be 10%. If you kind of always think of exponential functions as being a function that grows at a fixed percentage growth rate, that will always be true. And any type of quantity that either grows or declines at a fixed percentage growth rate can be modeled as an exponential function. Okay? We'll give you a couple of examples. Sometimes we'll use different letters for the parameters, but we'll always have the same form. Okay, so let's say, for example, that prices are rising over time. Anything that you buy, prices rise over time. So let's say the cost of a machine is now $1,500. And let's also suppose that the cost is going to grows at, say, 3% per year. All right, we can write down an equation, C of t. We're going to use C for cost. Okay. I'll put 1,500 down here. That's the initial cost right now. You can think of that as the y-intercept. Okay. And then the b is going to be 1.03, 1 plus the r. Okay, if I got 3%, my r is going to be 0.03. And then my exponent is t, that's my variable. Okay. So this function can be used then to tell us what the cost would be in any particular future year. Okay, so we could ask, what does the machine cost, say, 4 years from now? All right, that would be, let's see, C of 4. Okay, we're looking at time 4. We'll have the 1500 there. We'll have the 1.03. We're letting the time be 4. So then you guys could do this on your calculator if you wanted to. If I take 1.03 to the 4th power, all right, I'm going to get 1.1255, rounded off a little bit. And then if I take that times 1500, I'm going to get $1,688, and I guess if I want to go to the cent, 26 cents. Let's do a quantity that declines over time. Okay, so let's say you're in healthcare, and we're going to look at dosages. When you administer a medicine, you have a certain concentration in the blood, or a certain concentration that you administer. That creates a certain concentration in the blood, and over time, your body eliminates that medicine, and the dosage declines. So let's say we have an original concentration for the drug. We'll call that D sub 0, just to make up a number. Let's just say it's 15 grams per liter, or some unit like that. Okay. All right. Let's say the amount decreases by 20% per hour. Okay. All right. Using exponential functions, our equation d of t would be 15 is the original amount, that's the a, and now instead of 1 plus r, we're going to go 1 minus r, because that's a decrease. Okay. The 1 is still standing for the original amount, but you have 20% less each hour, so you have that be a negative. Okay. And if we simplify that, that's 15 times 0.8 to the t. Okay. So then if we wanted to figure out how much is left after a certain amount of time, we could just put in the time for t. We just want to make sure we use hours as our unit. So let's say after 3 hours, we have d of 3 is 15 times 0.8 to the third. Okay. And again, you could do this right along with me on your calculator. We go 0.8 to the third. On your calculator, you would look for a y, a y to the x or x to the y button to do this part. When I do 0.8 to the third, or your regular calculator, 0.512 is what I get. and take that times 15, and that comes out to be 7.68. Okay. All right, we'll do a couple more examples. Let's see. Let's do one with compound interest. And with compound interest, and your Hawks will give you an equation for this. All right, so in this formula, the P is going to be an amount of money that you invest. Okay. The R, similar to before, is going to be a rate, an interest rate, but it'll be an annual interest rate. So R equals annual interest rate. Okay. The N is going to be the what are called compounding periods per year. Okay. If you have a savings account, typically you get your interest paid to you once a month, which would be 12 times a year. So if you have monthly compounding, N would be 12. If your interest gets paid to you only 4 times a year, then N would be 4. Okay? And then here, T will be a number of years. Okay? So let's say you invest your $1,000 that we did before at 10%, but now it's going to be compounded quarterly, right? Which means they will pay you interest 4 times a year instead of once a year. Okay. The equation, A is for amount. Okay. P is 1,000. We're using our same equation up here. Okay. We'll go 1 plus. The R is still 0.10, but since we're compounding 4 times a year, we're going to have divide by 4 there. And then the exponent, T is number of years. We're going to multiply by N to get the number of compounding periods. In this case, if we have 1 year, but 4 times a year, our exponent's going to be 4 times 1. Okay? So this will be 1,000, 1.025 to the 4th. And if we want to go ahead and calculate that out by calculator, we're going to get 1,000, and this 1.025 to the 4th is going to be a little bit bigger than 1.1, 1.1038. Okay? So we're going to end up with $1,103.80. Okay? The compounding earned us an extra $3.80 as compared to the previous example with this where we had the 10% but just paid once a year. Okay? Because you get your interest more often, you earn a little bit more money. Okay? All right, so that's a introduction to a few examples of using exponential functions as modeling functions, as applications. Compound interest will be one. In the next video, we're going to look at some further examples that will relate to section 7.2.